Hello, Internet. We are live.
Hey everyone, welcome to episode 44 of the Stanford MLSys seminar series. I'm Karan, and as always, we have with us Stan, Piero, Fyodor, and our guest today, Gideon Mendels from Comet ML. So as always, we're going to have a 30-minute talk followed by a 30-minute podcast-style discussion where you in the YouTube live chat can ask questions. You can continue to post those questions during the talk. We'll keep track of them and get them across to Gideon at the end of the talk. A little bit about our speaker today. So Gideon is the co-founder and CEO of Comet ML, which is a company that works on MLOps. Today, he's going to be talking to us about system design for MLOps, and specifically, I think, examining some naive machine learning workflows and how to apply some system design principles to that. So Gideon, take it away.
Awesome. Thanks so much. Really excited to be here. Really appreciate the opportunity to present. And I've been enjoying the Stanford MLSys series as a participant or as a viewer for a while. So it's just great to be here. And as Car mentioned, what I'll spend most of the time today is talking about machine learning system design, specifically for continuous experimentation. So just a little bit about me. I actually started I guess like a lot of you, started my career as a software developer about 15 or 16 years ago. And I shifted to working on hands-on machine learning about 8 years ago. So like you, I was a grad student at Columbia University, mostly worked on NLP tasks. Specifically, I was working on language modeling for speech recognition systems, while at that time, there was an acoustic model and a language model. I know that's no longer the case. And after that, I founded a company that worked and built a large-scale chat analytics lab called GroupWise. We got to deploy about 50 different models to production, fairly simple models, but in large scale. And after that, I was at Google. I worked on hate speech detection on YouTube comments. And one of the things that were really interesting, kind of working with these machine learning teams, both at academia, small companies and startups, and large companies like Google, is a lot of these machine learning teams looked a lot like what software engineering teams looked like 15 or 20 years ago when I started writing code. And this has been a few years ago and things have progressed. But like if you think about the software industry, we have this amazing stack of tools like databases and testing, monitoring, orchestration, deployment, logs, the whole thing, right? Each one is like a multi-billion-dollar industry with a bunch of commercial vendors and open source. But then a lot of the ML teams, definitely back then and still to an extent today, use scripts, notebooks, emailing notebooks to each other, using Excel to manage their workflow. And it doesn't mean that you can't be successful that way. It's just much, much harder. And that's really what got us to start Comet. And as Car mentioned, what we do today is we essentially allow machine learning teams to manage the entire development workflow of models. So all the way from tracking your experiments, data sets, results, and so on, to monitoring these models in production. We've been around since 2017. We're backed by some Amazon, a bunch of other VCs, and we power some of the best ML teams in the world, like Uber and Etsy and a bunch of others. From day one, we actually give and continue to give free access to academics. So if you're a student and working on your paper and want to give it a go, please visit us at Comet ML. But specifically, what I want to talk a little bit more about today is just kind of like the current state of machine learning in the industry, right? And specifically, I want to have a particular focus on teams that have models in production and why it's important, this idea of continuous experimentation. So we'll dive into some case studies from the field, and we'll try to spend some time highlighting examples of these production-specific challenges and solutions. And finally, I'll try to tie everything together and offer some thoughts on where we see ML system design going in the future. So when we started the company in 2017, and I talked a little bit about it, one of the biggest challenges for machine learning teams were really building models that actually work well enough. As you know, taking a research paper, applying it in an industry use case is really, really hard. And especially if you're trying to meet some business or product KPIs. So we decided to focus on what we saw at the time as the highest impact pain points that help teams and companies build better models. And what it looked like in 2017 specifically is a set of tools that allow you to track and manage experiments, debug models, and being able to get reproducible result. But 4 years later, and working with all these customers, we start seeing them face new set of challenges. And while machine learning production is definitely not a new concept, the ecosystem around it is actually still very, very early. So we often see these diagrams, and it makes it look like the entire problem is solved, and you just have to kind of apply it in your company or team, and everything is figured out. But what I want to do today is actually talk more specifically about some of the challenges you might face in production, and maybe how we've seen other and how we recommend you should try to approach solving them. So specifically, let's dig a little bit into this. What are some examples of challenges that are endemic to having models in production? I'll give you a hint, it's not just about data problems. And we're also going to look at some challenges that are unique to models in production, and some solutions. So, and again, because at Comet, we spend a lot of time working with the great machine learning teams, we're trying to explore this from the lens of field studies, case studies, from leading machine learning teams in the industry, less from an academic perspective. And it's our belief that by inspecting it this way in more detail, and as well as approaching to solving it, we can provide some leading indicators how most teams will design their ML system, and specifically MLOps systems in the near future. So generally speaking, there are a lot of bad things that can happen in production, but here are some of like the top challenges and issues that generally we see teams report, right? So the first one is like, how do you even know you have an issue, right? So we'll get more into the details in a bit, but like looking at something like model drift is great, but to detect drift, you have to compare it to distributions. Which distributions are you comparing? Is it this week to last week? Is it the last 24 hours to the same period last year? Really not a trivial question to answer. The second thing is it even possible to get labels in production to evaluate the model? And if so, can you get them fast enough so they actually make a difference? Second is, your models can fail abruptly, but unfortunately, which is sometimes better, believe it or not, but can also actually slowly degrade over time. And what does failure really look like? So it might be easy to detect a catastrophic failure. You'll see it in some downstream product or business dashboard. But in most cases, your model will first fail on a subset of the data. So they don't usually fail uniformly. So, and from a business and product perspective, failing in one segment isn't always equal to failing in another. And we'll get into this in a second. But let's go through a few examples, and instead of kind of talking very high level. So the first one, we picked the most challenging, or probably one of the most challenging production environments, where a model mistake can be catastrophic. And of course, as you can tell from the photo, I'm talking specifically about self-driving cars. The majority of the source and content for this section actually comes from Andres Karpathy's recent talk on his team efforts. If you haven't watched it, I highly recommend. There's a link here in the bottom. I'm sure I can share that with you over chat as well. But of course, like just to set up the context in a very high level, the general idea here is that we're trying to build a self-driving car, hopefully getting it at some point to a level 5. Now, one thing which is actually a little bit tangent to the production side of things, that one of the approaches that they took, which is very interesting, is they built the car with all the sensors and tech and cameras and everything you need to do predictions, but they did that way before they even had the first model. So again, this is a little tangent to the monitoring production side of things, but it's just it's a method to bootstrap data collection. And in academia, sometimes we can work through like academic data sets, so they're like easy to come by. But in industry, like getting good training data is sometimes like 90% of the battle. So this method of bootstrapping, I think, is very interesting. And maybe if you're trying to do something similar in your company or your job later, you could apply some of these methods. But I think one of the questions to ask is, why do they need such a large data collection pipeline? And if you ever try to model something in the self-driving car realm, you might have an idea. So what Tesla noticed like very early on is that even if they had fairly good performance metrics during offline training and evaluation, they still run into issues in production. So in this case, production training data skew is not always avoidable. And specifically, most of the areas of the data describing is around edge cases and more specifically out of distribution samples. So as you can imagine, if you're thinking about, again, about the use case, in self-driving car, edge cases are extremely important. You need to perform well all the time. And really, you can't afford missing out on certain segments. And the challenge with edge cases, again, by nature, they occur fairly rarely. And this, of course, touches the high-level kind of concept of machine learning generalization. I will not try to attempt to solve this in this talk or even go too deep. But of course, for those of you who are not aware, maybe not proud, generalization discuss how your model will perform in data that it hasn't seen during training. And there are approaches, offline approaches, to try to evaluate how your model is going to do that. For example, you can try to simulate out of distribution samples by withholding certain scenarios during training. But at the end of the day, all of these are just proxies and approximations. And out of distribution and edge cases can also pose a challenge with offline evaluation. So models can perform very well in aggregate, but not in edge cases. And offline evaluation strategies are fundamentally limited by the fact that they rely on historical data. So while it's key to have a robust evaluation strategy, at the end of the day, you need to deploy the model to production. Deploying to production is key. This is where the model needs to perform well. And so what Tesla did here, which is actually very interesting, is they deploy what they call shadow models, right? So the loose definition of a shadow model here is a model that's running prediction like any other model, but those predictions are not being served or really acted upon, right? So they're basically just storing the prediction in some kind of database. And then what they're doing is they're using weak signals and heuristics. For example, the autopilot disengages because the driver kind of grabs the wheel. And they label that using essentially weak labels as potential mistakes, and eventually downstream it helps them to identify model failures and edge cases. So they take these weakly labeled samples, they go through their data cleanup, processing, labeling pipeline. But what happens next is interesting, right? So I'm guessing a lot of you would expect, okay, I got a new set of labels. Let's just retrain the model, right? Well, let's make it completely automatic because we have a way of generating these weak labels. We can use human annotators to make them strong labels. Let's just run an automatic repipeline. But while clearly to solve this or improve this, you do need to retrain the model. It's actually not a trivial problem at all. And I'm specifically referring to retraining. Now, in this case, right, like how do you deal with these new outer distribution samples is actually crucial. It's a form of this like balancing act, right? So if you try to boost these new samples too much, you can start witnessing things like catastrophic forgetting, where, the model suddenly no longer performs in sample it used to when it can now, but it might do better on these what used to be out of distribution. So, thinking about the use case, it can now navigate roundabouts, but can maybe no longer drive in freeways. And if you don't boost these samples enough, the new task is not learned by the network. So the main point I'm trying to make here is that like what often people call today is like offline experimentation is not this thing that you do once, put in production, and then you have retraining pipeline completely autonomous. To be successful with machine learning, specifically in industry, you have to always bring back production data and results offline to like your workbench so you can build these better models. So I'm going to switch gears to a completely different case study, but also another one that talks about some of the issues you might face in production. I'm sure a lot of you heard this concept of drift. So in addition to what we saw with Tesla, which is a form of trained production skew or data trained production skew, drift is a common challenge teams face in production. It comes in many, many shapes and sizes. As you can see, it could be sudden, it could be gradual, it could be recurring. And each of these types of drifts actually impact how you should think about solving them or eventually solve them. So in some cases, you might want to build a completely new model. In some cases, you need new data. Sometimes it's just retraining, unit testing, and so on. But let's dive into a specific example. So this is a great case study that I love specifically, and it highlights data drift. And it comes from one of the leading dating apps. If you're single and been dating, you probably use this app. And it's just a use case that my team knows very well. And in this case, the machine learning team there were tasked with building a user verification model. So try to minimize fraudulent and fake accounts on the app. And from a base mix perspective, given a photo uploaded from the user, try to detect whether the photo matches the user profile. So, kind of like a standard computer vision classification task. Now, the team built the model, they put it in production, and everything was great for a while, right? So you can see in the chart here, this shows model performance over time, and everything was great. And suddenly, as you can see around month 4 or so, performance starts to drop, and it ultimately drops by about 10%. And just to give you a sense of the severity of this problem, in their case, a 10% drop in performance results in about 10K manual moderation tasks for the support team each day. So this is extremely expensive and painful for the business. And as many people probably expect, you got a deep in model performance. As long as you can collect more labeled data samples, you just run automatic retraining, right? All good. Unfortunately, not really. So when they try to retrain the model, it had little to no impact on model performance. And I'll pause for 2 seconds if you want to start try to think what could be the case here, and I'll tell you what actually happened. So just take a sip of water. Try to think why retraining wouldn't help here. Right, we have different performance, collect new data, retrain, still low performance. And it took the team actually a long time and many cycles. So don't feel bad if you didn't get it in 2 seconds. But eventually, by manually investigating, they debugged it and figured what actually happened. And it was the new iPhone. So they realized that the new iPhone camera, which came out right around the same time, they started seeing model deterioration. And the camera resolution was so much higher that the data coming to the model was, higher dimension, more information rich, more pixels, and so on. The model couldn't actually represent it. They did try, downsampling techniques and such, but that actually didn't help. So they actually needed to go back and re-engineer a completely new model. In that case, adding a few extra layers to account for this new information before redeploying it. So again, you're starting to see this kind of theme that automatic retraining is not enough in most cases. They had to return to model development stage from production, build a model, and it's very common. Production introduces factors outside the scope of your modeling pipeline, and you'll have to account for them by returning back to development, or what people often call offline, and going through things again. So switching gears for the third and last case study, showing a different issue you might have in production. So this is from Slack, actually. And what it really shows is that monitoring aggregate model performance isn't always enough. So in many cases, with machine learning, the business KPI does not align with the machine learning performance metric that you're using. So, and honestly, generally speaking, in most cases, aggregate performance doesn't really matter. What really matters in industry is what the business team or product team care about. So whether it's a downstream business or product KPI, and the only way that you can get close to this is trying to build granular performance heuristics on the model. So in this case, what you can see in this chart, we have this big customers, and unfortunately, they decide not to renew, specifically actually complaining on one of the model results. But the team is looking at model performance, looks fine. Yes, there's some seasonality, but overall, this looks okay. And you can see that even though in this chart, you can see that the aggregate performance is fine, but the specific performance on that customer data is way off. So this is not, it says customer model performance. It's not a separate model. It's one model that serves for the entire population, but specifically that customer segment is underperforming. And that's why it's so critical to look at model performance across different data segments. And some people call the technical term segmented analysis. And the reason segments are so important because there's really 2 main reasons. First one, you want to try to align the business KPI with a machine learning metric. So 2% drop in performance for a large client about to renew needs to be surfaced. And when looking at the aggregate performance, this is often lost. The second thing is by using segmented analysis, by looking at specific segments, it actually helps you identify the root cause problem. So when you identify a 5% drop in performance, it's unlikely that all predictions are affected the same way. Most of the time, it's just this subset of predictions that are seeing a 10% plus minus drop in performance. And in order to really dig deeper, look at the data, you need to have segments. So everything I've been talking now is from like a production monitoring perspective. But an interesting part here is if you have specific segments that you care about in production, you should definitely try looking at them when evaluating the modeling offline. So not just look at your aggregate metric, try to look at these segments in offline training as well. So what's common to all these use cases, right? So in all these cases, in all these problems, eventually the solution comes from looking at what typically people call as production monitoring, and offline experimentation is very closely related tasks. And in fact, like, we think that experimentation is part of production. The closer you can get these things together, the better your machine learning system will perform. And the bigger the gap, the harder it'll be to be successful. In fact, like, we spent a lot of time speaking to customers and users and thinking about this. And this, I would call artificial split between offline and online is something that the machine learning industry in many ways inherited from software. In software, whatever you're building and doing locally is extremely different than what happens behind some application server, behind an API in production. But in machine learning, whether you're predicting on your offline data set or doing it in production, it's mostly the same thing. There's obviously some differences and challenges, but at the end of the day, if you want to look at it from an abstract perspective, it's just a different stream of data coming into your model. So let's try to bring these two things together, kind of like. So I'll start with monitoring, right? So there's a lot of solutions, open source, commercial. I'm not referring to one specific, but just give you a sense what typically monitoring products in the market offers. So first thing, they allow you to measure model performance or accuracy metrics. Lots of challenges with that. Data reconciliation, if you do have a human in the loop that provides labels, typically those will arrive after the prediction is made. And if you're trying to compare and know how well you're doing, you need some kind of baseline to throw an alert or retrain. Data drift is like a really, really hard problem. It might be easier in some modalities, but things like images and text are actually very, very hard to do. And again, how do you compare it to what happened in training? Third thing, which we talked about, is segmented analysis. Not all data is equally important. And then you got the more kind of, I guess, low-hanging fruit features, but which are typically very helpful, is like a prediction search. So you can pull in a specific prediction from production and try to debug and view what actually happened there. And of course, on top of all of that, you might need some kind of alerting capabilities. So this is what typically people call production monitoring. Now, if we think about experimentation, so these are things like tracking your hyperparameters, your metrics, your results, visualizing predictions, trying to debug the model by looking at confusion matrices, looking at your loss curves converge, hopefully, during training, and really just trying to compare these things between models and experiments so you can build better models. And eventually, like on top of that, you typically have some form of collaboration. But what gets really interesting is when you start putting these two things together and you start looking at the intersection of here, right? So in fact, like the features, the use cases that people are trying to solve for in production and experimentation, like have a very, very high overlap. So at the end of the day, we're looking to evaluate the models. We're looking at the dashboards, alerting, and understanding how well our model performance is, what are the errors, and what we can do to fix it. And in fact, actually, we think that in the future, what today is called experiment management and model monitoring will actually become the same category, because how closely these things are and how much value you can bring by doing this, like 1 + 1 = 3. So hopefully, I was trying to give you some sense of what it looks like in the industry and why we think bringing these two things together. That's all I have for today, so I'm happy to answer any questions. Thank you so much.
Thanks so much, Gideon. Thanks for the great talk and walking through those case studies. We have a bunch of questions in the audience. Just a reminder to folks in the YouTube live chat, keep those questions coming and we'll get those across to Gideon at our end. So just to kick things off, maybe, it's kind of a provocative thing that you say at the end, which is that, these two kind of separate categories where there are a lot of companies that either offer model monitoring solutions and a lot that do experiment management. Maybe there's not a need for the two. Are there ways in which you think, beyond just capabilities, like as you pointed out, a lot of the features that you need to provide are similar. Are there also ways in which you think, actually developing those solutions, kind of there's similar things that you need to do at the back. Because for example, for an experiment manager, people use TensorBoard, for example, right? And it's you can code up your own experiment manager. A lot of people in the old days used to you just log stuff to CSVs, and that was basically kind of doubling for that. So, but most people I think couldn't develop a model monitoring solution in research course. I'm just wondering, like, to someone as a researcher, it seems like one seemed a little bit harder than the other. I'm sure you've thought about this. When you're developing those two, are there things that are actually very much in common when you're building those?
Yeah, that's a great question. And I agree that in some ways, monitoring is harder than experimentation. So, but in some ways, it's the other way around. So for example, in monitoring, as you can imagine, like being in a production environment, we're talking about like throughput of data and how do you do that in scale. And that's, definitely not a weekend project, right? And experimentation, it's not necessarily around that kind of kind of scale problems, but there's actually a lot of things that could cause a lot. So I'll just give you maybe a very specific example, right? Like if you're trying to monitor your loss curve during training, right? And you're trying to report it as you go. If you don't do it the right way, you will slow down your training job quite significantly, right? Especially with Python, with the GIL, like you can really mess it up, right? So yes, if you just write the CSV at the end of the job, that's fine. So I think both of these categories have a lot of pain points in them. I think that around experimentation, it's a lot harder to surface actual results. I'm not just talking hyperparameters and metrics, actually surfacing things to the researchers that helps them drive the next step of research. So
my laptop crashed, so if you give me a second, we'll be right back. Don't go anywhere. Meanwhile, how's everyone doing? I actually don't have the chat open, so I'll get it back as soon as I can. All right.
Hey, Dan, so you're
hey
streaming.
guys,
You're streaming your room,
I'm
and
back.
you're not blurred out, by the way.
I'm aware. Yes,
Yeah.
I had this as a backup option in case.
Okay, great. No worries.
Yeah. No, it's because I use Zoom to blur myself. Yeah. All right. Let's see if I do this.
You are streaming right now. I don't know.
All right. I think we are back for real this time.
Okay. Awesome. I'm gonna toss it over to Piero and let him get the next question.
Right. So I have a couple of questions. Maybe one that I'm particularly curious about is, Gideon, from your experience working with multiple customers, one of the aspects you touch upon that I think is really important, and also, Karan here did a lot of work on that, is like, this idea of slicing and monitoring on specific slices of data so that you make sure that at the granularity that you care about, that's where you figure out what potential issues happen in each single slice of data that you care about, right? I imagine that, for specific customers, that identifying these slices boils down to domain knowledge. So I know my domain, I know my customers, and so I figure out what the slicing is there. But I'm curious if there is something that you've seen that actually applies across customers, like a methodology for identifying these slices that is something that is more general and could be widely applied.
Yeah, 100%. And that's a great question. I think you're right. Like the domain knowledge is where slicing by domain knowledge is probably where you see the most value. But generally, like what we always try to do is to try to give value out of the box, even before you customize these things. So some of the things that I guess are kind of like the low-hanging fruit, I would say, is like slicing your data by features, and specifically within feature, like certain thresholds. The other things that we've seen popular, and that's a little bit more specific, is if you have if you have an entity of a user that you're making the prediction against, is looking at some of the user attributes. So for example, their country of origin, their browser, their system. So for example, in the dating app example, looking at the iPhone model will probably tell you a lot. That it wouldn't tell you it's the camera, but it would tell you it's something with this iPhone version.
Yeah, that makes a lot of sense, and thank you for your answer.
I'm just one quick follow-up on the the case study you had was really fascinating, just because it shows that in production, a new iPhone appeared, right? It's the real world, and like weird things happen. I'm just curious, what if any takeaways you had about how to better monitor data for production settings from that case study, because I can imagine that it is possible to catch that error, but you'd have to obviously know it ahead of time. Maybe you're thinking about, the resolution of the raw images before they get pre-processed and so on. So I'm just curious if you've taken some lessons from that.
Yeah, 100% right. That's like something that's so easy to write a unit test for, right? Like, check the resolution, number of pixels, like the easiest thing ever. But the problem, like you said, is like you never know these things beforehand. So that's why looking at, for example, so if you start from the top, like in that case, you'll look at aggregate performance metrics, that's typically lagging. But if, for example, they're using segmented analysis and monitoring these segments, and you can set alerts with like simple heuristics, X points from standard deviation or something like that for each segment, you are risking the case of having too many like false alerts, and then people stop looking at that. That's like a more behavioral problem. But by kind of slicing the data into different segments and setting alerts on it, you can typically actually identify these things before they have a major impact. Typically, some cases it's too difficult, but that's what we've seen some customers do.
Okay, yeah.
Actually, still in the Slack use case, was it Slack? No, sorry, the
dating app.
The dating app, yeah.
Yeah.
Actually, when you ask the question, right? I was the answer that I gave myself was a change in behavior from the specific users that are the ones that were trying to trick the system, right? Which in this case was not the case, but I can imagine that it could be also another category of potential failures or potential reasons for the decrease of performance for over time, right? So the users that are trying to trick the system adapt to it.
Yeah.
Right? And so curious if you have encountered this kind of cat and mouse kind of situation in customers that you worked with, and if yes, what could be like potential ways around it, whatever you learn for the use cases if you encounter that.
Yeah, so I don't necessarily think that customers who use the monitoring product have seen these like adversarial examples. So I don't know if I have the best answer there. I would probably argue though that in that case, the shift won't be as large. It won't impact such a large amount of, unless it's automated and a bot, but that there's like other mechanisms to detect that. But yeah, I know like when I was doing hate speech at Google, I know like abuse was a huge problem, like one of the biggest problems, I would say. And I think every product that gets big enough identifies that. It could be that specifically with our customer base, it's less of an issue, or they haven't communicated back to us.
No, that's very important because, I guess that I can imagine that there are specific applications where they are specifically designed for those kind of adversarial use cases, which maybe have some slightly different characteristics from like general one, like the one you're describing. So it makes a lot of sense.
Hey, Gideon.
Yeah, go ahead.
There were a couple, I think, interesting questions in the audience. One was from Sanjeev Kumar, kind of what are the triggers to decide whether you want to retrain a deploy model, kind of start re-engineering the features and rebuilding the model? What's kind of that triage process that goes on, in your experience or that you've seen work particularly well in the field?
Yeah, I think to be honest, like with a lot of things in machine learning, it's extremely task dependent. Task dependent, infrastructure dependent. So I don't want to give a misleading answer here. But I mean, generally speaking, if I am trying to think of a very simplistic approach to it, if retraining helps, sure. I mean, it's typically an easy from a human intervention perspective, it's an easy task to go through. Although in some cases, in some use cases, the models are so big, retraining is extremely expensive. So it's actually the last thing you want to do. But typically, if you actually look at, so when I walk through some of the feature set that monitoring solutions have is around log search or prediction search. So if you look at some examples where, for example, if you have ground truth data, great. If not, maybe cases where the model confidence was very low. By looking at those things, you can typically eyeball some of the issues. So generally speaking, trying to be careful here because it's so task dependent, but I'll avoid that. I don't want to mislead anyone, and especially computer vision, tabular data, NLP, such different things. But the key thing is having a system or a way to visualize and understand that there is an issue. I would start there before trying to figure out automating the whole thing.
Yeah, that's really interesting. There's another question in the audience from Shreya Shankar about kind of a couple of those case studies, like I think in Slack and the dating app in particular, you identified kind of this online-offline environment gap. It's kind of the cause of the problems. What would you say is what kind of sticks out about you as from those particular use cases that like really makes you think that that's the particular gap, and how do you kind of identify that from, one of the other million things that could go wrong in machine learning these days?
Yeah, so I don't necessarily think that the issue or the gap between offline and online is the underlying issue or the reason why the model broke. I mean, I think in one case it was training and production data skew, and the other case it was data drift. But what the point I was trying to make is by closing that gap between these two workbenches, if you want to call it that way, you could actually iterate like significantly faster. Because if you feel like iteration offline is painful, when you have a model in production and you're trying to like go through it, it's typically extremely hard. It takes such a long time. So closing that loop gives you fast iteration cycles, which gives you eventually better models.
Gotcha. Yeah. I'm seeing more and more audience questions stream in just to, complete the trifecta about all three case studies. We just got a question, how did Tesla fix the challenge that you talked about in the beginning? One of our audience members feels like you left them on a bit of a cliffhanger there.
I left them on a cliffhanger. So first of all, I don't, just to be transparent, I don't work for the Tesla AV team, and I'm assuming if they solve all their solution, they might not go public about everything. Essentially, so I'm trying to go back to the slides. I think the questions of, and I'm assuming that's what they're referring to, the question of this balancing act of how do you introduce out of distribution samples and retrain your model or fine tune on it while avoid catastrophic forgetting. Catastrophic forgetting in general is like a large academic topic that I don't pretend to have all the solutions for, but I think what the point I was trying to make is there isn't a magic solution here. You have to experiment, you have to iterate, you have to try different things. And that's why you essentially have to go back to the offline training environment. So I think, maybe I'm being a little bit repetitive, but what I'm trying to say is like, you can't automate this entire thing perfectly. Like, in order to be successful, you will have to go back and like look at the data, look at the samples, retrain. It's just part of the job, unfortunately. I mean, maybe one day, and I think Tesla alluded to it, they said, we hope that one day our machine learning engineers can take a 6 months vacation, basically saying they can't now, right? Which tells you what they're doing at that time. So I know it's not the best answer, but I'm just trying to reflect how painful it is out there in the industry.
Right. I imagine if they solved it, we'd have self-driving Teslas all over the place by now.
Yeah.
I'd love to kind of follow up on something Piero was talking about recently, which is kind of the need in many of your examples to kind of demonstrate the need to monitor all of this, like essentially cross product between possible inputs and outputs to this system, right? Inputs is the data, outputs is its performance, maybe if it's a classifier, performance on different, classes, etc. I'm wondering, are we relying too heavily on machine learning engineers to be able to specify, concrete unit tests that do this kind of thing? Wouldn't it be better for them to just specify every possible like data dimension that could go wrong, whether it's like pixel size or the, roughly the amount of pixels in a particular area of the image that's black, for example, right? Maybe that has an effect on downstream performance. Couldn't we do that, programmatically after developer specifies all possible dimensions. Is that even tractable? What do you think?
In a sense, I think it's almost like a philosophical question, right? And you can use the analogy of software engineering, right? Like when you do test-driven development, or you're trying to write unit tests for your system, like that is what you're trying to do. You're trying to come up with all the possible kind of unit tests that might fail eventually in production. But someone who's been in software for a long time and seeing my software engineering team, typically what happens, you encounter an error that wasn't covered, and then you add the unit test. So it's just very hard to think of all these different dimensions. And of course, if you go completely abstract, it has to have an image, sure, right? Like you could do that, but eventually it's just this trade-off between how specific it is and how helpful it is.
If I can chime in on this, I think also the other dimension is many testing for machine learning implies, as in many cases, not always, but in many cases, has a cost which is substantially higher than testing for general software, just because each single test, in particular integration tests, can be very, very expensive, right? And so it's always, at least in my experience, a balancing act between coverage and feasibility of testing, and it's always again, it's a zero-sum game to a certain extent, right? So it's kind of difficult.
That's really interesting, Piero. I'm wondering, Gideon, do you have a sense? Are people currently playing this balancing act? Would they want to test more, but are limited by cost at this point?
So Pierre, you're referring to the cost of essentially running a set of prediction tests, or what cost specific? Are we talking like GPU, or the time it takes to build these tests?
I would say the combination of the two, right? If you have, integration tests and they take days to run, obviously that's not feasible and it's not practical in general. And also, if you have to run them on GPUs, and if GPUs cost a certain amount of dollars an hour, then testing becomes so expensive and again, you want to have tests that make sense, like check for performance, check for correctness, all these things. But at the same time, you cannot do it in an extensive way. You cannot test all the data sets. You cannot test all the metrics and all the combination of models, right? So that's why I was saying it's probably like a balancing act between coverage and expensiveness.
Yeah, 100%. I think we're seeing that similar things in the software world as well, where unit tests are cheap, integration, smoke tests, and maybe visual UI tests are extremely expensive. And then typically software teams, you might run a unit test, the unit test suite every time you create a pull request, but only when you're doing kind of a major version deployment or a minor version deployment, you run the whole set of tests. So yeah, I think, generally, I agree with the statement. Yeah.
Yeah. And also I think there's a dimension which is modularization, right? You can unit test some little modules. The problem is for me, your implementation of multi-headed attention could be absolutely correct, but then in the end, it doesn't matter because in the model that you're training is not performing as well as you were expecting. And so there's this tension with different dimensions of correctness and different dimensions of what makes a test pass that machine learning specific, right? And that makes the problem slightly more difficult, in my opinion, of what a regular software project may have, right?
Yeah, 100%. Just another complete layer on top of all the challenges you have with software, both in training and in production, by the way.
Yeah. We actually had a question about that in the audience. How do you unit test a model? Like Piero said, your attention layer works fine, but is there anything, better than just, run the thing on some val set, cross your fingers? Do you have any tricks up your sleeve to see? We had a question about multivariate drift in there. So how do you test these things besides if I'm Slack and my customer left? Yeah.
Yeah, so specifically, I remember when, unfortunately, I don't get to train a lot of models these days, but at the time, for an example, when I was Google, the kind of best practices and specifically around training is one of the tests was to have a test that essentially trains the model on, one data sample. So try to go through the training loop at least once. There's other things but Piero said, even if your implementation, your model algorithm implementation is perfect, you still have this complete new you have all the data sides to it, so that's why it's so tricky. So I don't know if I have all the best solutions out there, But yeah, I know Pierre, we had a lot of conversations about this specifically fairly recently. You probably have more opinionated opinions than I do, but that's probably all I can add here.
Right. Yeah. There's I just saw a comment also in the chat about kind of the engineering cost of building all these things. You know, at the end of the day, if you're paying a team of engineers, you know, running your GPUs for some number of hours is like a fraction of the cost of hiring a whole QA team, or you know, something goes wrong and then having to like spend a ton of man hours on that. Have you like noticed like those kind of like, I guess, like human dynamics in Comet and any of the you know, as you've been working on those companies? I think it's, you know, really interesting, but something that we don't see a lot in you know, discussions of like machine learning you know, typically.
Yeah, so just to make sure I understand the question, you're referring to the trade-off between kind of like the cost of having a separate QA team and then the engineering team doing it themselves?
Right. So just you know, thinking about the cost of, you know, how much it takes to, you know, collect data or design good tests, or have a dedicated team of QA you know, personnel evaluating and running and figuring out the how well these models kind of work in practice. Just, you know, balancing all those factors if you're trying to, you know, deploy these models as a real company.
Yeah, again, I think it's task dependent. I think a lot of the times what we call like QA in this case is really like just the data annotators in the loop. So maybe like to give a specific example, like the hate speech detection model on YouTube comments at the time, right? That this has been almost 5 years now. Did not actually flag comments, or so there was a classifier that said whether a comment contains or doesn't contain hate speech, the binary classification, but it didn't actually remove it. If something came back positive, it didn't actually remove it from the comment list. It went to a human moderator. So you can call that QA in a sense, but I guess what's interesting here, maybe when we talked about how everything is harder with ML, this is something that's, you know, kind of works in our favor, is by having this human moderator in the loop. Of course, you give the user a better experience, but on the way, you actually generate more training data. And especially for these, you know, out of distribution examples where confidence was very high, but still a mistake, typically. So yeah, very, very task dependent, but having this human in the loop, if you can figure out in a way that's cost effective, typically will help you build a way better model over time.
I'm just curious, you know, maybe shifting a little bit towards looking towards the future. If you've noticed some of the trends that we're seeing on the research side with, you know, training these massive models and pre-training and kind of having a single large behemoth model that you then deploy downstream for many different tasks, if that's something that you've seen, you know, across customers or generally in industry. And, you know, I can imagine that changes how you would address or tackle some of these problems that you've talked about in this talk and discussion, like, you know, data drift and stuff. You have to then worry about, is my upstream model, like the giant model that I trained, is that the problem, or is it, you know, situated in my downstream small model that I fine-tuned? So some of those, you know, situating the problem issues become more difficult. So just curious if you've seen some of those, you know, play out in practice yet, or if that's something that, you know, we should wait a few years to see.
Yeah, no, I think it's an interesting problem. I think it is probably like, you know, if we're talking about something like GPT-3, obviously that's kind of available by API just to a few selected members. So I haven't seen customers use that or the API in production. I'm sure there's some startups that do, but I think it's a little bit early. And, you know, the definition of behemoth is, you know, it changes basically every 6 months. But obviously we do see a lot of transformer models in production, but those are typically not as remotely big as GPT-3 or even GPT-2 in most cases. So yeah, we haven't seen these things, but I agree with you. I think like looking in the future, like it just makes things so much harder. And I think this in Tesla case, they have this one master model and a bunch of different heads, and right. So I think they're probably the earlier than everyone else kind of starting to address some of these issues. And they talked a little bit. I do recommend if if anyone on the crowd haven't seen that talk, it's super interesting. So, yeah, we definitely don't have a solution for it now, but it's also important to maybe to mention, and I know that's something that was very surprising for me coming from academia to the industry, is the state of machine learning in industry is probably 3 or 4 years before what you think it is. The amount of models that we have in production, and I'm excluding the Googles and Facebooks and Apple's, Amazon of the world, the big tech companies, the amount of models you see in production is actually quite low. And from those, the majority of them are, I would say, more traditional machine learning models, linear, XGBoost, things like that, less kind of fancy deep learning models. So, I think academia is so far ahead with papers, and that's amazing. I think that everyone benefits from that. But industry is really still struggling with some more simpler concepts of how do we even treat these things? I've seen challenges coming. I spoke to one of the largest banks in the world, and what they're saying is technically a machine learning engineer or a researcher, let's say we have a model that decides whether to give credit to a loan or not, could technically put in the training data samples and or if it in the fact that when that person submits a loan application, they will definitely be accepted. And then the modeler gives essentially a binary that waits to the production or deployment team, and they don't feel comfortable with that fact, right? So what they're thinking about is, no, the modeler will give the data set, the training recipe, and it will be retrained specifically for this case in production. So there's so many bigger questions that are less about architecture and the level of models. And I find both of these things fascinating, but just important thing, if you're a PhD student learning machine learning, coming and joining the industry, is typically the problems are a little bit different.
No, that is a great answer and a great perspective on where things are today, and hopefully we'll see, as you said, some of those issues ironed out first, and then some of them more things that in academia people worry about these days, pre-trained models and so on. Hopefully we'll have more answers for those as well as we solve these challenges. So thanks so much, Gideon, for joining us on the YouTube segment of this talk, and I want to thank everybody in the audience for joining in. As always, we're going to be back next week. You can go to our website, mlsys.stanford.edu, join our mailing list if you want to keep up to date with who we have on. We send out 1 email a week, so we don't really spam you much. Subscribe to the YouTube channel, and I think next week we have Baharan Mirza Soleiman talking about robust learning from massive data sets. So see you all.
Thanks, everyone.